Well, today we are going to discuss projectile motion. Projectile is a new word for us here, and since we're studying its motion, we should probably define what is a projectile. Really, the only characteristic for a projectile is something that's moving in three-dimensional space, and it's not under any propulsion. So this is an object that can't move itself, and it isn't currently being forced. It isn't having any acceleration acting on it. So examples of projectiles, well, a bullet would be a projectile. If a bullet is shot, once it leaves the gun, there's nothing forcing it, and it tends to take this arcing kind of path to Earth. A rocket, once it leaves the launch pad and the engines are shut off, like an air-powered rocket like we've used in class, well, that's a projectile. It's not under any propulsion once its engines are shut off. It's a projectile. A ball, any kind of a ball, like a football or baseball, golf ball, once that thing has left its whatever's pushing it, an arm or a golf club or whatever, that thing is a projectile. A ski jumper would be another example of a projectile. Ski jumper goes down the hill, and then you've all seen these people like in the Olympics or something. There's your ski jumper. Once they leave that hill and they're no longer being forced by gravity, they are a projectile. So those all are examples of things that are projectiles. Well, here's an example of a real-life projectile. It's been videotaped. This is just a ball that's been rolling down a ramp. If you look up here in the corner, you can see this ball exiting this ramp, and the ball is going to fly like balls do in both dimensions, not under propulsion, which means that this thing is functioning as a projectile. Let's just watch it fly here in slow motion. You can see that it's moving in this kind of arc-like path, and if we analyze this a little more closely, we can learn a little bit more about its motion. Now, what I'm going to do is set this up in this software here so that I can keep track of it with some numbers. I've got a little tape measure here. I'm going to drag one end of this tape measure up to this meter stick that I've got taped to the wall here, and I'm going to take the other end and drag it to the other end of the meter stick, just so that the software knows what a meter is. So I think that I got that about right, and now I'm going to tell it that is 1.0 meters. So now it knows what a meter is, and now we're going to analyze this, and I'm going to just put some coordinates on here. There's its first move, second spot, third spot, fourth, fifth, sixth, 7, 8, 9, 10. I can track 11 spots before this ball moves off the screen. Now, if you look at this just generally, it seems to be that as you go in the horizontal direction, there isn't much change in the distance covered per step. It also seems to be that if you're moving in the vertical direction, well, the amount of distance covered per step is increasing a bit. The distance between 10 and 11 vertically is certainly much bigger than the distance between the 0 and 1 point. Let's do a little analysis. Over here I've got a graph of time versus x, or distance in the horizontal direction. You can see that it's pretty much a straight line. Here's another thing that I can graph. This is y versus time. Well, that doesn't look very straight line at all. In fact, it looks a little parabolic. Let's analyze both of these. Here's my time versus horizontal displacement graph, and I'm going to fit a curve to it. I'm going to click on Fit. I'm looking for a linear fit, so that's what I'm going to select. And I'm going to have it auto-fit my points, and there it is. There's the line. Now, this doesn't use the R-squared value. This software uses something called RMS deviation, root mean squared deviation. And the smaller that number is, the better, the closer you are to having zero error. And that's 2/1000ths compared with a value of 1.8 for our slope. That's a very good agreement. And if you look at the points physically, graphically on this line, the correlation is obviously very good. And so, in fact, it looks like in the horizontal, this thing is moving at a constant speed. In other words, every increment of time takes it the same distance farther away from the origin. Let's take a look at that y-axis movement. We'll also analyze that. Well, you can see that there isn't a very good linear regression. The RMS deviation isn't that good, and visually the fit looks not that good at all. So let's try a parabola, because that's what it sort of was looking to us like. And now we get an RMS deviation again in the hundreds. Very good correlation. And this is telling us that, in fact, the motion in the y-axis seems to be represented by a parabola. Now look at the value for A in this parabola. A is the coefficient of the t-squared term. It's 5.61. If I take 5.6, negative because it's going downward, if I take 5.6 and double it, well, I got something that's not exactly, but fairly close to the acceleration due to gravity. And if this object, in fact, is falling through a gravity field, I guess I'd expect the distance covered to be equal to the initial velocity, which I would hope would be 0, but probably isn't exactly for this trial, plus half the acceleration times time squared. That's our distance equation for something that's undergoing constant acceleration. Well, if A over 2, acceleration over 2, is 5.6, and I double it, I should get the acceleration. Well, it really is close to the value for G, and that's what I'd expect to see. So what we're going to do now is kind of look at an idealized version of this. This is a grid, and here's a kind of a little fake projectile that we're going to see move on this grid according to what looks to be what we're seeing from the real-life movie. There's the object moving. This is kind of a stylized projectile motion. Okay, now let's do this. Let's take a look at the horizontal movement only and separate it from vertical movement. With each time increment, you can see the line that represents horizontal motion going over an equal increment of distance. Let's try that for isolating the vertical. For each time increment here, we see not an equal movement in the y-axis. In fact, towards the end of the flight, we see quite a bit more movement in the vertical axis than we do at the beginning of the flight. Well, these are some numbers that actually are put on another recording that I took of a ball falling through space, a projectile motion. And this is my x-axis motion, and they're both on the same scale here. Just for comparison, you can see that very linear value when I do an XL regression here. R squared is 0.9984. That's telling me, yeah, the relationship between distance and time for the motion in the x-axis really is a straight line. That means constant speed, no acceleration. If I look at what's going on here in the y-axis, just like I had with the other piece of software, my dy, my distance in the y, follows a parabola. It doesn't follow a straight line, and the regression for the parabolic fit is very good. In fact, it's even better than it was for the linear, 0.9998. So that's telling me that, in fact, this is following some kind of an acceleration, a constant acceleration pattern. And our distance equation looks like this. Now, it didn't start at 0. It didn't start with 0 velocity, so there's a little error there. But if you look at the acceleration over 2 term, that's multiplied by delta t, which is what x is represented by here, because time is on the x-axis. Again, we have something that, if I double it, is really close to 10, which is approximately 9.8, the acceleration due to gravity. So what's going on here is this. In the horizontal axis, the projectile is moving at constant speed. So the math that we'd use to solve problems involving the horizontal axis motion is this. A very simple one that we learned a long time ago. The distance covered in the horizontal is going to be equal to the horizontal velocity times the time, and that's it. Distance equals rate times time. Well, that's very easy. If you know what the initial horizontal velocity is, it's the same as the horizontal velocity all the way through. Now, this depends on one simplification, and that is that there's no wind resistance. We're assuming that this is constant, that there's nothing slowing that down. That's not true in real life, but it's fairly close in a lot of situations and can make a pretty good model. In the vertical axis, however, the projectile we've seen is under constant acceleration, and that is the acceleration due to gravity. So we have two equations for dealing with this. When an object is under constant acceleration, we know that the distance covered during that acceleration is the initial velocity times the change in time plus half the acceleration times the change in time squared. Well, since a projectile is accelerated by gravity, we could model this instead as distance equals initial velocity times change in time plus g over 2 times the time of acceleration squared. And lots of projectiles, not all, but lots of projectiles are going to start out with that term being a 0, which makes some of our problem solving fairly easy. The other equation that we've seen that works for constant acceleration is that the final velocity during an acceleration is going to be equal to the initial velocity squared plus 2 times the acceleration times the distance. Well, again, in many situations, not all, but many, the initial velocity is going to go to 0, and acceleration is always going to be equal to g for a projectile, and so that means final velocity many times is going to simplify to this, 2 times g times d under the radical. So these two equations can be used for a wide variety of problem solving. Like this one. Let's try and solve this problem. A bullet is fired horizontally with an initial speed of 9,600 feet per second from a height of 1.5 meters. And the question here is, how long does it take to hit the ground? So here's our bullet. The bullet initially is moving this way at 9,600 feet per second. Well, that's a speed, 9,600 feet per second, velocity. And it's falling from a height of 1.5 meters. The question is, how long does it take to hit the ground? Well, it doesn't really matter how fast it's moving in this direction. That just tells how far it's going to go before it hits the ground in the horizontal. How long it takes to hit the ground depends on only two things. What was its initial speed and what's its acceleration? Well, the acceleration downward is g. Its initial speed, well, if it's fired horizontally, it wasn't going up, it wasn't going down, it was only going straight. So its initial velocity in the vertical axis was 0. We've seen that for projectiles in their vertical direction, the distance covered is related to the time by this equation. D equals initial velocity times change in time plus acceleration over 2 times the time squared. But that term is 0. We've decided that this didn't have any initial velocity in the y-axis, and acceleration is g. So the equation becomes this. D is equal to g times delta t squared divided by 2. So if I want to find time, how long does it take, I can solve this equation for time. 2 times d divided by g is equal to delta t squared. So if I take the square root of both sides, I find out that delta t is equal to 2 times d over g. Well, so now I just put some numbers in there. Delta t is equal to the square root of 2 times 1.5 meters divided by 9.80 meters per second squared. And then when I finally do my calculation, I will get seconds, because the meters cancel out, and the answer, when I calculate it out numerically, is 0.55 seconds. This is an expansion on the same problem. The bullet is fired horizontally. It has an initial speed of 9,600 feet per second. It's fired from a height of 1.5 meters. The question now is, how far does it travel horizontally before it hits the ground? Well, remember, horizontally, we only have constant velocity. And so we have the very simple equation that says the distance traveled is equal to the speed in the horizontal times the time covered. Well, the initial horizontal speed is 9,600 feet per second, and we found out in the last problem that it's 0.55 seconds in the air before it hits the ground. So when we multiply these two together, we'll find the distance that it's covered, and that turns out to be 5,280 feet.